This is a guide reading for Chapter 11. A lot of what you're going to see in this chapter is new, but there is some stuff we're going to get to skip over, so please follow along. So you need to open up your books, Chapter 11, page 301. And Section 11.1 is mass density, which is the typical density that you've been working with in your science courses all your life. So you don't really need to read this, density equals mass over volume, but do notice the equation and the symbol that they use for density. You should be familiar with that from physics. That's the rho symbol. Also, you may want to look over table 11.1 just to get some typical densities so you have a feel for gases versus liquids versus solids. And those are in terms of kilograms per meter cubed, which is what we use in this course. And of course, one of the ones that you should be familiar with is water. At 4 degrees Celsius is 1,000 kilograms per meter cubed. Before you leave this section, take a look at example problem 1 and make sure you can follow along with that. If you have any questions, let me know. All right, welcome back. Section 11.2, pressure, this is on page 302, has everything to do with the bed of nails that we are doing in class today and that you saw, of course, in physics. You may need to read this, depends on how well you remember that idea, but certainly I do want you to look at a couple pictures. Look at figure 11.1, and that's a picture of a tire. And they're showing that the air molecules are colliding with the inner wall of the tire and the outer wall of the tire. So there is pressure acting on those surfaces. When we talk about this pressure of force over area, if there's an area, obviously we're going to have something contacting that area. So in the terms of an ideal gas, we can consider it to be the pressure of that to be with the collisions with some given surface, not with each other. And then they have the directions of the arrows there being perpendicular to the surface on figure 11.1. Also take a look at figure 11.2. The woman swimming through there, the forces act inward on her from the pressure of the fluid everywhere. And of course, from physics, when we talk about buoyancy, we'll get to what those add up to and why there's an up arrow. That's it for section 11.2. Take a look at, before you move on, take a look at example problem 2. And you don't necessarily have to read all this, but look at example problem 2, and then look at atmospheric pressure at sea level and what that's equal to in terms of pascals in atmospheres. Okay, next up is section 3, pressure and depth in a static fluid. Okay, so this is for a fluid that is not moving, and that's the key thing here, not moving. And we did a little bit of this in physics, but it's going to get a little bit more complicated here, not a whole lot. When fluids are moving, that's when things are really going to change a little bit, okay? But because of some of the complexity of the problems, when you're actually having to figure out different pressures at different depths, you might actually have to apply some of the equations in this section, so you do need to read all of 11.3. And when you're reading, before you start reading, make sure you go over example problem 4, the swimming hole question, and pay careful attention to some of the concepts that are going on here for pressure with depth and what it depends on and what it doesn't depend on. Okay, so go ahead and read 11.3. Okay, welcome back. That was a lengthy section. One of the things I'm hoping you've got out of that is that if you look at the picture on page 305, towards the bottom, figure 11.8, that it does not matter if there's cliff over you or water over you. So yes, the idea of it's the weight of the water above you is what we used in physics, but obviously that's not completely true. If there's a cliff over you, it's really the depth you are from the surface anywhere in determining the pressure. Also, if you want to make an analogy to the air, okay, we have a pressure due to the air above us, okay. If a plane flies overhead, you don't all of a sudden feel the weight of the plane and get crushed. Same thing in the water. If a submarine goes overhead, you don't all of a sudden get crushed. So you can't truly just take it as the column of the weight of what's above you. Also, before moving on, I'd like to mention that if you didn't look at the conceptual examples in this section, it's important that you do so, as I think that will fill in a lot of the gaps. And their reasoning is somewhat detailed on those. So that should help out a lot. All right. So the next section, 11.4, pressure gauges. There's a whole lot here to convince you of something that actually is not too difficult once you've applied it once or twice. So I don't want you to read all this, but I do want you to look at the end result of the equation on page 307. Towards the bottom there it says pressure 2 minus atmospheric equals rho GH. Okay, and they're going to call P2 minus atmospheric the gauge pressure. Here's the idea. When you hook something up to like a tire, okay, if the tire's flat, what's it going to read? 0. Is the pressure of the gas on the walls of the tire, is the pressure of the gas at sea level really 0? No, there's atmospheric pressure, okay? But the gauge is calibrated to not account for that, okay? So it's calibrated at sea level so that you're really reading a difference there between atmospheric pressure and whatever the pressure is bigger than that, okay? Which is this idea that pressure 2 minus the atmospheric pressure is the gauge pressure, okay? And then that will equal rho GH, okay? If you didn't like that way of thinking about it, here's another way. Look at the equation right above it where it says pressure 2 equals atmospheric plus rho GH. That's what I was just talking about, that the pressure that is at sea level in the tire, the gauge reads 0, okay? So you have to take, if you want to find out the absolute pressure, okay, what it is, not accounting for the fact that the gauge is calibrated to 0, you'd have to take the atmospheric pressure plus rho GH, or in this case it would just be, in my example, atmospheric, okay? So either way of thinking about that, but it is the gauge pressure is the difference between the absolute pressure and whatever the pressure is of the atmosphere at that point, okay? So actually, please do read just those last couple sentences there about gauge pressure and absolute pressure just to make sure you're okay with that. And that one equation, that idea of gauge pressure. And that will pop up in problems from time to time on the actual tests. Okay. 11.5, Pascal's principle. We use this. We didn't call it Pascal's principle, but this is the whole hydraulic lift thing, or the brakes in your cars, brake fluid. This idea that a small area with a small input force, if you have a big area on the other side, you can get a big output force. Okay, and the equation 11.5 on page 308, I usually write that as a ratio. I usually write P2 or P1 equals P2, and then I substitute in F1 over A1 equals F2 over A2. They've solved. I would still recommend, like in physics, that you just write that the pressure of 1 equals the pressure of 2. And this uses the idea that, to a good approximation, liquids, okay, are not compressible. So that means that the pressure at one height has to be the same as the pressure at another. Now, what if the heights are different? Okay, now you have to take into account the pressure varies depending on the depth of the fluid, and that's something that we didn't do in these problems in physics. So take a look at the example problem 7 to see how to apply this new idea that there's going to be a difference in heights. So there's a corresponding picture on page 308, 11.15. You'll see the car, and this time there's a difference in height from where you're pushing on it to where the piston actually is, or the other area is on the other side, so the cylinder. Okay, so take a look at example problem 7 and see the differences there in terms of accounting for that rho GH in the problem, the different heights. Okay, all right, that was it for 11.5. 11.6 is Archimedes' principle, which is proof of the buoyant force. Okay. And I think you'll be able to follow along if you're okay with the rho GH idea. This is just a little bit of proof of the buoyant force. So go ahead and read 11.6 and take a look at example problem 8, which should look familiar. All right, welcome back. Example 8 with the raft was very similar to something I had you guys do on one of your physics tests, I think, for most of you. But once again, buoyant force is equal to the weight of the fluid displaced, which is the density of the fluid you're in times the volume being displaced, okay, times g. So the equation you read about there is that rho vg for buoyancy that we used in physics. Okay. All right. That's it for that section. Okay, there's a couple more example problems there. Hopefully you took a look at them to remind yourself how to apply that stuff. And there is a rho vg in those problems. Okay. Page 313, 11.7, fluids in motion is going to be skipped. Okay, we don't really need that, the viscous flow versus non-viscous. or viscosity. If you want to read that, you can. It's a very short section, but we don't need it. So take a look at 11.8, the equation of continuity. The end result is what we really need here, but the mass flow rates do pop up sometimes. So take a look at equation 11.8 on page 314, and they have rho A1 V1 equals rho 2 A2 V2. Okay. However, in most of our problems, the density of the fluid is not going to change. Like, for example, figure 11.27, the water, where they change the area of the opening. Of course, the water comes out faster when you put your thumb over it. But the density of the water is the same everywhere in the hose. As long as that's true, it becomes way more simple, and that is the equation we'll use 99% of the time. On the top of page 315, A1 V1 equals A2 V2. Okay, take a look at the picture. Do read 11.8 and take a look at the sample problems so you can see some examples of this being used. But don't get too hung up on the mass flow rate stuff. It should make sense, but most times you're going to use that AV equals AV idea. The area times the speed of the fluid equals the other area times the other speed. Okay, and we did talk about that some in physics. So now we got fluids that are moving. Okay, which brings us to the big part of this section, and that's 11.9, and that's Bernoulli's equation. Okay, you'll need to read 11.9 maybe twice. Okay, but before you do that, take a look at page 318, equation 11.11, 11.11. That's Bernoulli's equation. Now it looks bad. Okay, and yes, you do need to know this one, but I'm going to give you a way right now to hopefully get you so that you won't have to think too hard about it. Okay, first of all, 1/2 rho v squared looks a lot like kinetic energy. It looks like 1/2 mv squared, except instead of mass, we're using density. Okay, well, using that same idea, mgy looks a lot like potential energy, except instead of mass, we're using density. Okay, a mass over a volume. So it's kind of like, it's not the same, but it's kind of like conservation of energy. Okay, so we have 1/2 rho v squared on one side plus rho gy equals the same thing at point 2 later. Okay, and instead of writing this all out, you could just write equals a constant. Okay, because we're applying, like it's kind of like applying conservation of energy. We're saying it's not, these two things have to be equal. Okay, and you will see that on the equation sheet, that the left side of this equation just equals a constant. Okay, but it means you can apply it anywhere in the problem. Okay, but then the one thing you can't forget is the pressures at those relative points. So if you have 1/2 rho v1 squared plus rho g h1 or y1 equals 1/2 rho v2 squared plus rho g h2 or y2, however you want to label it, you have to also add in the pressures at those levels. Okay, so that's the way to remember that. They go through a little bit of proof on that using, of course, conservation of mechanical energy and work done by non-conservative forces and that kind of thing to get this result of Bernoulli's equation. So it does have to do with energy and work done, and hence the similarities there to conservation of the similarities there to kinetic energy and potential energy. You do not need the proof of that, but I think it helps you to understand this equation a little bit better. So go ahead and read all that section. You might need to go through parts of it more than once to try to get a grasp on what's going on there. Okay. All right, welcome back. 11.10 is all about applying Bernoulli's equation. Okay, and you'll see some things that are similar, like page 319. There's a picture of the two trucks and the trampoline thing going up. Okay. In physics, we talked about that example. I had you get a piece of paper where you blow across the top and the thing goes up. Various examples of the Bernoulli equation. So some of these are conceptual, and for the conceptual stuff, you already have it from physics. The faster the fluid, the lower the pressure. Okay, everything else being the same. Those ones are fairly straightforward, but applying the equation is the part that's going to be new. So make sure you look at not only the conceptual examples, but the example problems, which are all in 11.10. Okay. One thing I want to point out before you take a look at that is the picture on page 320 at the bottom can be misleading. Planes do get lift from the fluid moving faster above the plane than below it, but there's no path argument here. It's not because it's covering more distance in less time in the same time or anything like that. There's nothing to do with like a path argument. In fact, the airflow around a plane probably does not look exactly like that picture in A. That is a misleading picture for that. And there's something else that makes plane flies too, and that's simply the angle of attack, or the fact that the air molecules, in a very simple version here, the air molecules hit and then there's an angle, so there's a net force upward. They don't really hit, but that's the idea, that there's a collision with an angle, and the plane is the plane has its wing angled so that when it hits, there'll be a net force up. Okay, kind of like when you stick your hand out your window. Okay, if you're driving fast and you put it at an angle upward, you feel your arm try to lift away. If you put it at an angle downward, you feel your arm try to go down. Okay. So take a look at those examples and make sure you do the check your understanding 4 on page 321. That'll get a feel for if you conceptually have this idea of Bernoulli's equation. And then, of course, the example problems will walk you through how to actually plug in numbers and solve, or solve for variables. Okay. 11.11, you skip completely. If you're really interested in it, go for it, but it's not. Viscous flow is not something that's on the test at all, viscous or laminar or any of that. So you can skip over that. 11.12 is some additional sample problems. It's up to you if you want to take a look at those. I think there's at least one where we've got some plug and chug, one where there's buoyant force, and there's one where you're applying summation of forces to a problem, and torque and a whole bunch of other stuff. So if you want to take a look at that, you can. A couple of fairly in-depth problems. Okay, that concludes this very long guided reading for Chapter 11. It was intended that we did this in class, though, so you should have had class time to work on this. That's it.